Hi guys, welcome back to Data Every Day. Today we're looking at a data set of Indian food dishes, and we'll be trying to predict whether a given dish is vegetarian or not, based on a series of features, including the ingredient list. You can see we have prep time, cook time, flavor profile, course, state, and region as our features, and we'll try to predict whether or not it is vegetarian. So, let's just get started. I have a notebook here. And you can see I've written task for today. Given data about different Indian dishes, let's try to predict if a given dish is vegetarian or not. And we'll use a TensorFlow artificial neural network to make our predictions. So I have some basic imports going on. We have NumPy, Pandas, Matplotlib, and then for preprocessing we have the label encoder and standard scalar, and train test split function, all from sklearn. For our actual model, we'll be using TensorFlow, as I mentioned. Alright, so let's start in by reading our data. So I'll use pandas read CSV function to grab the CSV file and get the file path right over here, paste it in there, and I forgot to import. So there we go. Then check the data as soon as that is done, and we should see just what we saw before, but now we can process it. So let's think about this. Alright, the name is not going to help us today, right? That's not giving us any useful information when trying to predict whether it is vegetarian or not. So we can just go ahead and drop that. And I also want to note, I feel like maybe the ingredients feature is cheating in a way. Because, like, let's say, alright, how about we make it into a real feature? Alright, so let's start preprocessing. And actually, let's just check for null values to start, just to get a sense of data. Looks like we have one null value in region, but region is going to be one hot encoded, so that's fine. One hot encoded, null values will just disappear. They'll be encoded as all zeros, which is just fine. So we won't have to worry about that. But okay, so let's construct a series of features, one for each unique ingredient in ingredients. So to do that, I'm going to create a set called food vocab, and I'm just going to add every unseen ingredient to the set. So we're going to iterate through the ingredients column, and then we're going to iterate through each recipe, and then we're going to add that particular ingredient to the food vocab if it's not already in there. So I'll just quickly code that up. For ingredients in data sub-ingredients. So this ingredients thing is one of these lists, right? For food, it's an individual food in ingredients dot split, comma, and you can see they're comma separated, so we can use this. And then if food, which is a single one of these between a comma, dot strip, so remove white space from the front end, dot lower, so that they're all lowercase, is not in the food vocab, then food vocab dot add this thing right here. Alright, if we run that was very quick. Just check food vocab. You can see every unique ingredient is now in a set, and the reason I use a set here is because it doesn't allow duplicate values, so it's a good way to ensure that doesn't happen. Even though we said this, it's probably not going to happen anyway, but it seems like the proper data structure. Alright, so now let's create a data frame using each one of these as a column. Okay, and so if let's say called food columns, we'll just initialize a new data frame, and then I want to iterate through this thing again, and each time I'm going to send this to a new column. Okay, so the food vocab was just sort of to show. I'm trying to think if we're actually going to need it. No, we will. Okay, right. So, for I and ingredients, so I'm going to enumerate the ingredients column. I know I misspelled that. Give me one sec. Enumerate. So this way we can use I to locate a row and column location in our food columns. So for food in ingredients.split, this is basically what we're doing up here, right? You know, I could even just copy that, but so split the comma. So this time if food.strip.lower is in food vocab, then we're going to index a location using the loc function of the food columns data frame at row I, and the column name is going to be food.strip.lower. Right, and we're going to set it to 1. And so what we should now have is a data frame with all the rows, and each column is one of these, and only ones where it's basically like a one-hot encoding, but it's not one-hot, it's like multi-hot encoding. All zeros, but there's ones for every, like for example 0 would have a 1 for Maida flour, a 1 for yogurt, 1 for oil, and 1 for sugar, but zeros for all the others. But right now it's not zeros, actually it's null values. So we have to fill in those null values with food columns dot fill na 0. Alright, if we take a look at food columns now, it's exactly like I said. There's 365 columns, each for a unique, let's see, length of food vocab. There's 365 unique ingredients, and now we have 365 columns where each example has ones wherever that if the ingredient is present in the recipe for that example. So the reason I'm saying this is using this as feature data is like cheating sort of, is because there's certain elements in here that are going to be non-vegetarian, right? And they're sort of like complete giveaways. If the model picks up that there's certain, like for example, if it says I don't know, chicken in here, if an example has chicken, it's automatically non-vegetarian, right? So I don't know. What I'm going to do is I'm going to train a model first without the food columns. I'm going to see how that does, and then I'm going to include the food columns in another model and see if that does any better. Or worse, you know, this maybe just adding the higher cardinality may decrease the performance, but also maybe not. Let's see what happens. Okay, so now we have our food columns. We're going to set that aside. We're actually going to drop the the original ingredients column from data, along with name and ingredients. So right up here, name we don't need, ingredients we're not using now, so we'll be left with just this part of the data set. So data equals data.drop. And not found, oh, I forgot to specify the axis. Okay. Alright, so now data looks like this. And what I'd like to do is now start encoding the columns. And before I do that, I'd like to get a sense of what kind of data is in each column. It's like, I don't know, is there just sweet? Is there 2 values? Is there 3 values? I can't see from just looking at this. So I'd like to make a dictionary that's going to map a column, which would like a column name, to a list of the unique values of that column. and that's going to be for each column in data.columns, but only if the data type of that column is an object. So essentially what I'm saying is get all of the categorical features. Remember, so these would be excluded because their data type is numerical. And then show me all the unique values in each of those. Okay, so as you can see, we have diet, region, diet, flavor profile, course, state, and region. And you can see the only binary feature, not even a feature, only binary column here is the diet column, which is what we're trying to predict. So what that means is we can use one-hot encoding on all four of these. Four of these. However, before I start, I notice that there's a -1 in, looks like 3 of them. And what I want to do is turn those into null values, because -1 I assume means null value, but it wasn't encoded as such when the data set was created. So I'm just going to turn them into null values so that when we one-hot encode, we can avoid having to make an extra column for -1. So that's not very difficult to do. All you have to do is say data sub, and by indexing twice like this, I can get a data frame subset of the original data frame. And there's 3, flavor profile, state, and region, in which we have -1 flavor profile, state, and region. And we're going to do dot replace. We're going to replace a -1 with numpy.nan. Alright, and then I'm just going to set that equal. So now if we check this again, we should see the -1s are gone, but now we have NANs instead, which is much better. Yeah, okay. So I'm going to make a function for one-hot encoding. Just call it one-hot encode. It's going to take in a data frame, a set of columns, and a set of prefixes to use for those one-hot columns, dummy columns. I'll start by making a copy of the data frame. Then for each column prefix pair I'm going to zip up columns and prefixes so that we can get pairs. We're going to make a dummies data frame using pandas.getDummies, and it's going to be the dummies created from this column that we're iterating through the columns, right? And we also iterating through the prefixes. So I'm going to make the prefix equal to prefix. Right, so for each one, we're going to make a dummies column, a dummies data frame. And then we're going to concatenate that dummies data frame onto the original data frame. Along the column axis. And when we're done, we're just going to drop the original column from which we created the dummies. And return df. Alright, and this is the only function we're going to need. I made it in such a way that we can pass in multiple columns and prefixes together. So all we have to do is say data equals one-hot encode, data, and then here, I'll put it like this. So I'm going to pass in a list of columns I want to encode and then their appropriate prefixes. So the columns I want to encode are going to be everything except diet, because diet is a binary column and it's also our label column. So I'm going to use the sklearn label encoder to encode that one. So flavor profile, course, state, and region. Alright, and then we're going to assign prefixes for each one, and they'll get zipped together. So if you're not sure what zip does, it basically, I'll express it as a list. If we zip two arrays, 1, 2, 3, and A, B, C, it will zip each element in order. So the first ones go together, the second ones go together, the third ones go together, like this. So what I'm doing here is I'm zipping the I'm zipping the columns and prefixes together and then iterating through in pairs. So let's make this the prefix F. This prefix for course will be C, the prefix for state will be S, and the prefix for region will be R. Let's run that, look at data, and it's fully label encoded. You can see the prefixes have been applied, and we now have 41 columns. Okay, I also noticed something. This has -1, and you can't have a negative prep time and a negative cook time. So I'm going to assume those are null as well. So let's go ahead and replace those with null values and then impute the means of that column since they're numeric. So we can do data, I'm doing the same thing I did earlier, prep time, cook time is just those columns. And if I do replace, this time numeric -1 with numpy.nan, should look like this, where the -1s have become nans. So I'm just going to update it to be like that. And then I'm going to do fill na with, actually I have to do it, I don't want to iterate through, I'll just do it twice. So data sub prep time dot fill na with data sub prep time dot mean. So I'm filling it in with the means, right? And we're going to do the same thing but for cook time. Alright. And oh, I actually didn't set them here. Okay. Now we should not have any null values and no -1 numbers. We should be ready to go. The last thing that we just have to do is encode this diet column to be 0 and 1 for our labels. So let's make a label encoder object, which will be sklearn label encoder. And we'll just say data sub diet is going to be transformed, fit and transform. So .fit transform. Sorry, that's not correct. It should be label encoder .fit transform. And we're going to transform data.diet. So now data should look like this. And sure enough, we have all numeric data. We're ready to split and scale. So I'll just get an idea of how these values were encoded by, I'll make a dictionary that maps an index to a label. And that's for every index label pair in enumerate the classes of the label encoder. Classes underscore is the attribute here. And you can see non-vegetarian has been mapped to 0 and vegetarian has been mapped to 1. And here is our data. I'm going to, let's say like this, splitting and scaling the data. So y is going to be data sub diet, and I'm actually going to make 2 x's. So like I said earlier, I'm going to train one model with just these features, and then I'm going to make another model using the food columns that we created earlier and see if it improves the performance of the model. So we'll make a normal x, which will be data.drop diet of axis, axis 1, And then I'm going to make one called xFood, which will just be the x with the food columns. And we can say pdduck and cat x and wait, it should be like this: x and food columns. All right, axis 1 looks good. Now I'm going to scale both these x's using a standard scalar from sklearn. So I'll make a new object, standard scalar, and then x equals scalar dot fit transform x. And we'll do the same thing for xFood. Alright, then we'll split into train and test sets. Xtrain xtest, ytrain ytest equals train test split xy, train size of 70%. And let's use a random state so that we can get the same for both of our data set, for both of our x's. So I don't know, let's use 42. And we'll do the same thing but for food. So I'm just going to go ahead and put in food on every one of these. Alright, that should be good. So we're using the same y but a different food, a different x. Alright, so run that, and now let's start training. And first we're going to do it with no ingredient features. Alright, I'm going to make a function to create the model. And the reason I'm doing it as a function is because we want to make more than one model here. So instead of having to write out the whole model architecture both times, I'm just going to make it once, and we'll call the function to create the model for us. So I'll call it build model, and we're going to pass in the number of features that we want for this model, and we'll also give it a variable called hidden layer sizes. That'll be, we'll default it to be 64 by 64. So we'll keep 2 hidden layers, but we'll be able to specify a number of nodes between the models to see if, for example, there's a lot more features in the food model, so we might need to up this to prevent overfitting. So inputs equals tf.keras.input, and the shape here is going to be the num features. There's going to be a vector of length num features. So like that. Then x is going to be our first hidden layer, so tf.keras.layers.dense, and the number of activations will be given by hidden layer sizes sub 0. Whoops. Sub 0. Right, so this first one. And we'll pass in inputs, and we'll do the same thing for the second one, but we'll pass in x, and this will be 1. Then for our output layer, we will make another dense layer, layers, and this will only have 1 activation since it's a binary classification in both models, and a sigmoid activation. Oh, I also realized I didn't put the activations here. Both of these should be activation ReLU. Okay, here we pass in x. Alright, then we'll compile the model. So I'll actually make the model first. Model equals tf.keras.model. And using the input layer as the inputs, and the output layer as the outputs. Okay, then we'll compile our model, model.compile, and we'll give it an atom optimizer, a binary cross entropy loss function, and for metrics, if you notice over here, I'm not sure, yeah, look over here, it says there's 89% of them are vegetarian. So accuracy is not going to be a great metric to use, because if we classified vegetarian 100% of the time, we'd get an accuracy of about 90%, which is it looks like our model's doing well, but it's not completing the task at all. So I'm going to use two metrics. I'll use accuracy, but I'm also going to use the area under the receiver operating characteristic curve, tf.keras.metrics.auc, and that's much more resilient to skewed classes and gives us an idea of how our model is performing across different classes and across different classification thresholds. Alright, so we have two metrics we're using, and now we can return the model. So we'll make the model, compile the model, and return it, and then we can fit the model that comes from this function. So we're going to be dealing with the first non-ingredient model first. So we want to create a new model with build model, but we need to know how many features to use. So we're going to find the shape of x, and we can see x has 40 features. So we'll pass in 40 for number of features, and hidden layer sizes, let's start it with 64 by 64. Okay. And yeah, we can leave this. This is the default. We'll say model equals build model 40 for the 40 features. Then we'll give it a batch size. Let's do 64. A number of epochs, which will be, let's just start at 100. And I'm actually going to use a callback function to reduce the learning rate upon a plateau, which will allow us to converge very nicely at the expense of the risk of converging to a local minimum. So I'll show you in just a sec. So this is model.fit. So xtrain, ytrain, validation split. We'll make it 20%. Then batch size and epochs given by what we have above. And then, yeah, I'm going to include this callback function, which will be tf.keras.callbacks.reduce LR on plateau. So what this does is when it notices that the loss has stopped decreasing very rapidly, it's going to reduce the learning rate. That will allow us to settle in very nicely to whichever minimum it is found in the loss function. However, if it's not the absolute minimum, if it found some local minimum, it's going to converge right into that, and there's very little chance it's going to get out of it. So we're going to run the model a few times to try to get the absolute minimum. But this is just so that it also allows us, if we use this, to train on a large number of epochs and not have to worry about overfitting, because the effect of overfitting over time is greatly reduced by this callback function. So it's a trade-off. But alright, so let's train it. Alright, and let us plot the results. So I'm going to use matplotlib to make a new figure with fig size of 10. We'll do 20 by 10 because I want to plot two graphs right next to each other. Epochs range is going to be our x-axis here. That's going to be a range from 1 to the total number of epochs plus 1, since range starts with 0. Then train loss and val loss, I'll just assign them at the same time. It's very similar. History.history sub loss and history.history sub val loss. And then I'm going to do the same thing for the AUC. So this, and this is going to become AUC. So I'm now going to plot two charts, one for the loss and one for the AUC. So we'll make two subplots. First one will be in a 1x2 grid. This is the first subplot. plt.plot epochs range on the x, train loss on the y. I'll give it a label, training loss. Okay, then I'll do the same thing, but for validation. So validation loss, and over here, val loss. Now I'm going to make another subplot that is going to, this will be the second one, and this won't be a loss, this will be AUC. AUC, and AUC. Alright, and then I'm going to put the legend on both of them. And plt.show. Oh, I should also put titles, probably. Let me just do that. plt.title, loss, and plt.title, AUC. Okay. So, looks pretty good. This is what I was talking about the converging. You can see the validation loss does not start to go back up. Instead, it just flattens out into this like absolute. It's not budging, right? Because the learning rate just got so small, it's just staying right there. There may be some overfitting, but really very insignificant if there is. And it looks like by the end here, we should have a pretty decent model. So let's see how it does on the test set. So model.evaluate x test, y test, and wow, it is not doing very well. Looks like it is. However, we're getting the AUC of 0.5, which let's take a look. X test, actually y test. Let's just look at the length of y test. 77 examples. So out of 77 examples, that's still pretty substantial. We're getting only, you know, it's not exactly a percentage, right? But this, you could think of this as being half as good as we want it to be, because an AUC of 1 will mean we got everything correct, and an AUC of 0 means we got everything incorrect. But it takes into account how we're doing both on the positive examples and the negative examples. So this is about 50% of the performance that we're looking for. And you can see the accuracy is about 87%, but like I said before, there's 89% vegetarian. So it's not a valuable metric for us. Very interesting though, on the validation set, we are getting validation accuracies of 100%. And what's even more interesting is that the training accuracy is lower than the validation accuracy. Well, sorry, AUC. I mean, the accuracy also is 100%. They'll go hand in hand. But this is very interesting, right? Why is the validation... Well, it could also be that it's just because we have very small number of examples in the validation AUC, I mean in the validation set. But let's try bumping up the size of the model, the architecture, actually. So we're going to pass in hidden layer sizes, 128 by 128. Let's see if this has an effect. Oh, sizes. Okay, so that's going to train. And take another look. Doesn't look very different. And we're still getting just a very poor performance on the model. So, let's just turn this back, because it did not work. Let's see what happens if we remove the callback function. What? Oh. Now this will change the way our plot looks. However, it's actually not. I think we should train for a few more epochs. Let's do 300. So that we can see when it starts to overfit. Alright, now we can really see. So it goes down, and then it starts to really go back up. Okay, so if I stop this around, we can actually get the minimum here. np.argmin validation loss. And let's print, we'll also print the argmax of the validation AUC. So what the argmin, argmax will give us the epoch at which we have a minimum here on the orange curve, and the epoch at which we have a maximum here on the orange curve, which looks like it's going to be like 1 or something. And we get 41 and 0. So interesting is, well, it makes sense. The longer this trains, the more our AUC goes down. But notice how it's going down in these increments. That's because there's not enough examples in our validation data, right? This is the difference between one example misclassified. A huge jump. So I'm going to stop it at 41 epochs. So we're going to train for 41 epochs. And then we're going to check the results. So this should converge right down like it was doing before. We evaluate, okay, we have 0.7 or so. So I'm not sure if I'm going to push it much further. There's just one more thing I want to try before we move on to the other model, which is let's bring the callback function in for back in, and let's set it to 300 epochs, which is something we didn't do before, which will give us it'll be training for longer, but it's not going to jump back up. Like I said, this will just converge right down. Looks like 41 or so is still lower though, right? So it looks like the optimal number of epochs here would be 41. If we check this, okay, we got 67. So not as good, but almost. So let's keep it the way it was before. Alright, we're going to drop the callback. Right. Make this 41 and drop the callback function. Alright, and one last look. This converges, and 0.685. So pretty good. It looks like that's the best we're going to get. I don't know, there might be other ways we could go about it. But now we're going to try it with the food ingredient features and see if we can get something better. So let's create, we'll say retraining with ingredient features. Like that. Alright. And so we're going to make a new data set. Oh, actually no, we already have xfood, right? So xfood is scaled already. But it's basically, if we look at the shape, it's the same number of examples as before, but we have 405 features. So we're going to make a new model. We're going to call this one food model. That's going to be using that same function build model, but the number of features here is 405 as opposed to the 40 we had before. So this is many more features, and also much more like there's very like core. There's features in here now that will really tell the model whether or not it's vegetarian. So I'm just going to copy the same code I had up here. Where is it? All this stuff. I'm just going to rename a bunch of the variables. These we'll call food. Is this food model? We'll call it food history. Xfood train. Oh my god. Okay. Food history. Food model. Xfood train. Y food train. Oh my god, I messed up again. Give me 1 second. Okay, like this, 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 this. Here, here, and here. Okay. Food underscore. There we go. Alright. So that should give us a new model, now with 405, and let's train for 200 epochs. And let's see how it goes. Food batch size. But I just... Oh, right. This one isn't. Okay. Alright, and I'm just going to copy the same thing I had for the matplotlib thing. Grab this. Results. And I'm going to change a bunch of this stuff too. So food epochs range, food train loss, all these will become food. Food epochs here. Food history. Food history. Food. 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 Okay. Hopefully that works. We had a problem. Food validation AUC. What is this? I misclicked. Alright. Okay. And it looks very similar to before. Let's see. Okay, so there's something here. There's a minimum, very sharp minimum, and it just starts going up right away. So let's get the, where is it? We had before, right here, this line. I want to get the epochs at which we find the minimum and maximum. So this will be food val loss and food val AUC. So 7. At epoch 7, this is at its minimum. So let's train for 7 epochs, see how this goes. That does not look very good, right? Interesting. Notice that before, the loss was at a minimum at 7, but it hadn't reached its maximum AUC yet. So, let's see how it does on the, so food model dot evaluate on x food test, y food test. And we have AUC of 0.61 now. So, you know, that's remarkable. I mean, because we only trained for 7 epochs here, right? Let's train again for 200 and take a closer look here. I have a theory about what's going on. I have a feeling that our hidden layers are too simple for this number of features. With 405 features, we're going to need something more than 64 activations per hidden layer. So if I look at this again, like we saw before, by the time we get here, even though the loss is lowest, the AUC is not very high. 7 looks like something like this. So let's see if we evaluate it now. 0.79. Now that's better than any model we've had before, right? So it looks like because this is still a very untuned model, we're still getting, before we could barely get 0.68, right? Now with these food features, we're getting close to 0.8. But I want to see, okay, let's try a few things. First, let's try increasing the hidden layer sizes. So we'll make it 128 by 128. Alright. And we get 0.88. So that's really good. We're actually getting a very nice model performance here. But I'm trying to think, is there anything we can do to improve it even further? So let's try putting that callback function here. See if that makes any difference. So now it's plateaued much more cleanly, but we don't know if we got the absolute minimum. But it looks like we're doing even better, 0.9. Fantastic. This is really good. I'm not sure if what we can do to improve it at this point. 0.9 is very good. If we look at the graphs, it's very interesting. What do you notice about this? The validation curve is still under the training curve. And here, the validation AUC is higher than the training AUC. So I wonder if this is underfit. In any case, it looks like this food model is doing just a much better job. I mean, it has a lot more data to go off of. It actually has the ingredient data to make a decision whether it's vegetarian or not. Yeah, I think that this is a good place to stop. We got a very good performance of this one. Thank you so much for watching the video. If you enjoyed it, be sure to subscribe and hit the bell, and leave any comments in the section below. I'll see you guys tomorrow. Have a fantastic day.